Hi friends, thanks for joining this open session on 5G and our key technical aspects. This session was delivered by Dr. Shrikant, who is the Chief Knowledge Officer for Nanocell Networks, and we have got more than 700 participants in our session. I hope you all enjoyed the session. If you have any further question, please feel free to write us an email at 5gtraining@nanocellnetworks.com. If you enjoyed the video, request you to visit our YouTube channel, like this video, subscribe our YouTube channel, as well as press the bell icon for the early notification for all our future videos. Thank you very much, and let's get started.
Acknowledge on the chat box. Thanks everybody. So let's get started after all those announcements. So this is a short introduction into some of the key technical or technology aspects of 5G new radio, as it's called. My name is Shrikant, and I'm with Nanocell Networks. And you have heard, of course, lots of things from Sanjay about various programs and initiatives. So let me get on to the matter. So many of you already have seen a diagram like this, where you've been kind of introduced to the various objectives of 5G. I'm just using it to get started on familiar ground. So 5G is an initiative which tries to meet the ITU's IMT 2020 specs. And of course, as we know, instead of just focusing on voice and broadband, which probably falls in this category called as enhanced mobile broadband, we also have new categories which are being explored by the, you can say, industry, primarily to get into other verticals rather than just serving consumers with plain data and voice. Of course, already cellular technology has made its foray into the IoT world through some LTE extensions. But in 5G, we start with some you can say, very clear first steps in this area. Okay. And of course, in line with some of these expectations, we have numerical targets on a variety of factors. So you might have heard about some numbers with respect to data rates and latency, etc. So I'm not going to repeat all of that. Okay, there are overview presentations, a lot of public material, and my focus is going to be very clearly on the new radio, 5G new radio. Okay, and before I proceed, I do keep hearing some people saying I can't hear and so on. But unless Sanjay or Kuldeep tells me, I'll keep moving because some people might not have had the correct settings. So please keep checking your link. Organizers will prompt me in case there is a problem from my end. Okay. So as I said, my focus will be very clear in the next 45 minutes or so on 5G NR. And I would like to kind of organize my presentation along these lines. So I'll start with spectrum. Okay. And maybe give an idea of people talking about some millimeter wave, etc. here. What is the big deal about it? How does it influence the specs? How does it matter finally to some of the 5G objectives, etc.? And that will lead us naturally to a very important part of 5G NR technology, which is flexible numerology, which incidentally is not only to support the multiple bands, but also the consequent bandwidths and also some services. And closely aligned with that is the dynamic or flexible TDD, which I'll talk about just at the end of covering numerology. Your questions can come at any time, so just put them out on the chat box. Since there are people who might have budgeted their time for about 45 minutes to an hour, I'll focus on finishing the presentation and then rolling over the questions from the order in which they've come. Okay, so don't wait for your question to be put out at the end, etc. Just put it out. Maybe it gets answered during my presentation, maybe not. We'll take it up. Okay, so after I finish this flexible numerology part, which is very important, I would say the cornerstone of the OFDM changes in 5G, and align it with the various TDD options, I'll go to another area which attracts a lot of attentions, which is all the new MIMO approaches, hopefully clarify this whole beamforming terminology, etc. and then finish up with, I think, a very important initiative called bandwidth parts, which allow us to do some interesting things. I might add in a few other things. This by no means is a complete sort of, you can say, description of 5G NR. Because it's limited in time, I've taken certain critical aspects, and this is also to showcase our capabilities in that so that you can hopefully sign up for some of our training in the future. So let me start with spectrum. Remember that I talked about how wide ranges of spectrum. So typically, for example, I'll cover, for example, the FR1 and FR2 is the language of 5G, where FR1 roughly ranges from this kind of spectral ranges. This is close to what we have encountered in previous cellular generations. So there is nothing dramatically new about this frequency range. The only thing is probably we are venturing out a little bit further than what we have ventured out in LTE, leading to larger bandwidths and the consequent benefits of that. Maybe there are technology impacts of how we can pack more users in this FR1 in a given spectrum. Okay. But I think the spectrum wise, the more interesting part is FR2, sometimes also referred to as millimeter wave band. This is the dramatically new high range spectrum that cellular is embarking on. I'll justify a few reasons very quickly. One of the cornerstones of every generation has been going to new spectrum. When you look at the 3G and 4G to a certain extent, etc. 5G, I think, is more dramatic because this is the first time we are jumping away from the comfort zone of single-digit gigahertz to double-digit gigahertz, possibly in some future releases also to hundreds of gigahertz. Okay, remember that if we are not going to be very successful in whatever way that we will define success, uh, the whole wireless business is going to be constrained by the fact that we are limited to this frequency. So that's not necessarily a good thing. So it's very important that somehow we find some nascent success, maybe not all what we aim for, but at least some important success steps need to be achieved here. So I think this is a very important step, and the technology interventions that we are doing here are very significant for our future UK foray into even more higher spectrum. Okay. So remember the first slide, which says that 5G is not driven by a single application. There are multiple applications. There are multiple types of deployments, different drivers, and even the usage of spectrum to a certain extent could be tailored to certain application deployment constraints. Specifically, what's new about millimeter wave? So millimeter wave is giving us the scope for very large bandwidth channels. Today we fight for, as we know, in the 2G days, we were, hundreds of kilohertz bandwidth channels to megahertz, maybe tens of megahertz. And now we are embarking on hundreds of megahertz, possibly leading to some gigahertz spectrum. Why is that important? Because remember that bandwidth is the cornerstone for high data rate. So if we are able to get large bandwidth channels, the chances of getting high data rates become that much more feasible. Okay. And unlike previous generations, remember I said 5G is thinking along very different lines. It's not thinking about only the access network, but also potentially even backhaul network. So don't forget that. If you think, oh, why do all my phones need multi-gigabit per second data rates? Don't think only phones. Okay. Think about even backhaul between, say, small cells and so many other things. Okay. And don't think only mobile deployments. It could be the broadband. It's like a fiber to your home. So those kinds of, you can say, ideas also are encouraged by some of these millimeter wave advantages. Of course, with every potential advantage, and these are some of the spectrum regions, even in fact 24 gigahertz onwards, there are lots of challenges, right? This is the first time we are embarking on a sort of consumer revolution into these kinds of technologies. Many of these bands have been used for very specialized applications, maybe for some point-to-point, highly engineered sort of links. And now we are going into links which are not that well precisely engineered, right? So obviously we have to tackle the lots of challenges ranging from environment related challenges to device and the consequent cost complexity challenge. So exciting times, because remember I said if millimeter wave does not get off the ground in 5G, then we might not grow as much as we could. And if that's the case, then we are stuck. You might say we are stuck in some kind of a sub 10 gigahertz kind of spectrum zone, which is not good for you can say the overall growth of wireless. So having given an idea of some of the things coming up, let's talk about the technology. The cornerstone of 5G technology, remember, it has to cover multiple bands, it has to cover multiple applications and multiple scenarios. But we want to make a base technology which can be easily tunable at the finest level. So the choice is an OFDM based waveform. So OFDM based waveform, but with a lot of flexibility. Remember, the OFDM is some of the granular units in the whole radio technology, and we want to make that flexible. What are we making flexible in that OFDM technology? We are making what is called as the subcarrier spacing, which is a very fundamental parameter in OFDM. And instead of a fixed value, which was the case in LTE, because remember LTE was primarily geared for mobile broadband, now we are in different zones. We are making that flexible where it can range as of today from 15 kilohertz to 240 kilohertz in some steps. And in the future, I expect it to go down to as low as this value because we already have some LTE IoT extensions there, and to some larger subcarrier spacing, which is mentioned in the early releases of 5G. How does this help us? This helps us from variety of angles. Okay. Remember, we said that for millimeter wave, which is the high frequency FR2 region of the spectrum, large bandwidths are the more enticing things which will help us to get large data rates. However, to manage that large bandwidth, we also need large subcarrier spacings. Why? From multiple angles. If we take the large bandwidths, and if I use the same subcarrier spacing as LTE, remember LTE bandwidth is 20 megahertz maximum. With 15 kilohertz, we could manage the so-called FFT sizes for the OFDM transceivers. Now, if I'm going to 400 megahertz bandwidth, and if I insist on having 15 kilohertz as my subcarrier spacing, that will blow my FFT complexity, which has to sit in every handset, remember. So reasons like that, hardware complexity at the very base level. Then comes RF effects, because the RF electronics at 25 gigahertz or 39 gigahertz, or in the future somewhere around 60 gigahertz, these are not going to be not as stable as say something at 2 gigahertz or 3 gigahertz. Okay, so because of this reason, okay, we also need the flexibility of the large subcarrier spacing. Okay, so these are some of the reasons why we need that flexibility, so that we can play around with large bandwidth channels in FR2, relatively smaller bandwidth channels in other places, etc. Okay, so I get requests for annotation. I'm just trying to not tamper with my presentation right now so that it doesn't have any effects on others. So just bear with me. So if we look at what does all those ideas translate into, if we look at today's FR1, so FR1 allows these subcarrier spacings, of which these two are mandatory, and FR2 allows these subcarrier spacing, of which these are mandatory. Okay. Now, if you're wondering, does 5G imply that a phone or a base station has to support both? The answer is no. There are probably 5G phones. I have not surveyed all the 5G phones, but many 5G phones might only support FR1. Some special ones do support FR2. And there could be the same company selling FR1 at one cost and then saying that if you want FR2, then like that same model or whatever it is, however they wish to sell, could be a different cost. So definitely we do have both supported, but remember, it's not always the case that both will be present in all devices. Again, please don't ask for any annotation request at this time so that it comes up on my screen. Please, let's avoid any disruptions at this stage. This was a very early stage contribution coming to the 5G standard, showing the vision of how the multiple subcarrier spacings kind of come into play. So this gives you an idea of the overall flexibility. So you can see that some cases it's in this case, the axis here is time and this axis is the frequency axis. So you can see in some cases the OFDM symbol is long, okay, leading to shorter subcarrier spacing. In some cases, the OFDM symbol is relatively shorter, okay. So you can find all cases, and here, for example, the subcarrier spacing is longer. So you could find mixtures addressing different applications. Do we expect to see this kind of a sharing in real life in the near future? Very unlikely, but we want to be forward compatible. We don't want to be caught napping when we have to do all these things in the same band at some time, okay? So definitely all this idea of flexible numerology is to also prepare us for future eventuality as well, okay? So if you look at the translation of that, this is just a pictorial view of how the numerology, we had one picture before this, we see another picture where you see the effect of the different subcarriers spacing, okay? So this is just going to show you how things pan out, just two different views of the same thing. So just to summarize, remember I used a 2 power mu in some of those slides. For those of you technically inclined, the mu is the factor which will control the subcarrier spacing. Mu equal to 0 defaults to the LTE-like subcarrier spacing of 15 kilohertz. FFT size, of course, will depend on the bandwidth. Looks like people want to annotate. Again, my request, please don't ask for anything right now, okay? You can have same bandwidth with different subcarrier spacings. We haven't yet seen people optimize on this front. So maybe you should, let's say we will wait it out. Once the standard has this in place, we'll wait it out to see how these numerologies will be used in a much more efficient way. Definitely today, the singular big use of the numerology is basically the you can say FR1, FR2. So in FR1, we are using one of this. In FR2, we are using one of this. Okay. Within FR1, are we using this intelligently, dynamically? We haven't seen large examples of that or within this. Okay. Now, remember the OFDM subcarrier spacing is the finest button you could say in the whole physical layer, and you are giving flexibility with respect to that aspect. Okay. Now we want to build on top of it. Remember that once you make things flexible right at the bottom, you can start, using that flexibility to have, multiple other flexibility at higher layer. The next is the resource allocation related flexibility. So as you know, from LTE onwards, we've been dealing with radio resources every millisecond, right? The base station or the E node B in the case of LTE, every subframe, which is 1 millisecond, it's also the subframe in 5G is also 1 millisecond. Frame, which happened to be in LTE as 10, is also 10. So both these are the same as in LTE, okay? But they don't necessarily serve the same purpose in the sense that radio scheduling granularity in 5G is not necessarily limited to a subframe. It goes down to what is called as a slot. So the slot in 5G is probably the most important thing from a radio resource allocation perspective. It's not fixed in time. It's actually fixed in number of OFDM symbols. Okay, so time is actually variable, and we'll see that examples in the next few slides. Okay, this gives us some flexibility with respect to handling certain services which might require, let's say, low latency, etc. So the ability of the whole system to support different OFDM symbol times, you see the ranges here, helps us to also construct granularity at the resource allocation level at different levels. LTE kind of granularity and much more finer granularity. Okay. So here is an example from referred from one of the vendors, giving us an idea of how people are thinking about how to use the different subcarrier spacing from a deployment and band perspective. As I mentioned, some of the low frequencies, you will see 15 and 30 kilohertz being used. Okay. Some of these high frequencies are typically, or rather higher subcarrier spacings are tailored for some of the FR2 deployments. And even there you see some targeted towards indoor, small cell, macro cell. So these are some of the, you can say, deployment related nuances that can come into play when you want to choose the appropriate subcarrier spacing and the consequent slot length. Remember, slots are not fixed in time. Here you can see that in one more visual form. Okay, so you can see different slot times. Of course, we talked about certain things being there in FR1 and certain things being there in FR2. Okay, and you can see that in the classical frame structure, the frame of 10 milliseconds is the same as it was in LTE. Frame does not have a great implication on the user's, you can say radio resource management, etc. It's more for system information, periodicity, and so on. Subframe in the case of 5G does not have great implication on the radio resource management, but the word slot is very important. In fact, the slot in LTE is fixed at 0.5 milliseconds, whereas in the case of 5G, it is not fixed. Okay, so when we have very low latency services, if you are in FR1, you're gravitating towards some of this, and in FR2, you're gravitating towards this. That's the idea. Okay. One immediate connection is how TDD becomes very flexible. So we have variable number of slot sizes, but then we also have other ideas to support flexible TDD. And this kind of summarizes the wish list which was put out, or the vision for the flexible TDD. Remember that in the case of LTE, where we formally introduced TDD as a part of the standard right from the first day one, you could say, we had fixed configurations, okay, downlink biased, uplink biased, etc. But in the case of 5G, we also have the ability to do, we don't have that configuration business. We have more of a, according to the nature of the situation on the ground, we could be heavy on downlink, heavy on uplink. We could even be offset from slot time because of carrier sensing kind of limitations which might occur in unlicensed band. Remember, you see within a slot downlink and uplink happening. This is again suitable for low latency. Bunching up slots for heavy download or heavy upload. So this kind of vision can also be realized with a flexible TDD. Okay. Again, you might not want to do all of this everywhere. So the G node B is very critical in defining what kind of TDD configuration. Usually we don't expect in a macro cell mobile scenario to have a lot of flexibility. The real flexibility at the granularity of a slot level is primarily going to come in some kind of a small cell scenario with few users where traffic can be very biased towards either downlink or uplink. Okay. Of course, we might see some low latency special cases as well where things could happen very dynamically. So there is cell specific and device specific patterns which the network can announce. And RRC signaling is typically used for all of this. This is more for everybody. This is user specific RRC signaling. And in these flexible slots, you could have, some information which will help us handle downlink and uplink in very interesting ways. There are, various possibilities here. And they are also useful for managing a lot of interference scenarios. Okay, so it's not just for data transmission, it's also to keep some people quiet when they would have normally transmitted. Okay, so example, just to compare with LTE is to see LTE had very fixed relationships. This kind of limited the latency performance of LTE. Whereas 5G has the bells and whistles where we can turn around very fast due to all those flexible TDD mechanisms, both on the downlink as well as on the uplink. Okay, we do have some videos comparing 5G NR with various LTE things on our YouTube channel. So I have had a look at the numerology. I have extended it to look at the whole resource allocation. Now I'll talk a little bit about the Mimo aspects in NR. Okay. Now, Mimo is not new. LTE had a very successful implementation of Mimo, right? And I would say spatial multiplexing and diversity, both were used very effectively in LTE. But now we want to move it to another space in NR. And I would say its demands of FR1 system and an FR2 system are slightly different. Remember that in FR1, we do not have as much spectrum as we would like. In FR2, we have lots of spectrum. Probably we don't have the coverage that we desire. Okay, so definitely for meeting that coverage in FR2, we have a very elaborate description of multi-beam, which is the most exciting technology-wise thing, very critical for FR2 systems to succeed. Okay, and in for FR1, we also want to increase what we call a spectral efficiency. So using very detailed channel information, which comes from reference signals, which are applicable for both cases, I would say we go deep into the channel information and leverage it for some very interesting spectral efficiency enhancements. Okay, and I usually find that MIMO is where a lot of misinterpretation happens. It's natural because there are a lot of things thrown around by people. Now, in general, in FR1, where we have had, in that region where we have been successful with what we call single user MIMO, base station to one user in one resource block, and similarly on the uplink, to multi-user MIMO, where base station covers more than one user in the same resource block. Okay, so this is the exciting new technology in FR1, and in fact, to achieve this, we embark on what we call as massive MIMO. This is again a term which is thrown around a lot these days. I see in popular literature. Basically, it refers to the fact that we invest lots of antennas at the base station side, which is potentially possible. Not so easy on the client side. Remember, the clients are handicapped by their size and the fact that power, aesthetics, all that come into picture. So we throw a lot of antennas at the base station side. People are these days talking about 64, 128, etc. And if we are successful commercially, and I think at least initial results seem to indicate that, there's no reason why this number will not be jacked up to thousands of antennas. Remember, theory has already shown us that these are possible. It's just that practical algorithms and their implementation are still some are going to keep us in hundreds of antennas or large tens till we get everything worked out. Okay, so as you can see, the idea of massive MIMO is to have large enough antennas with enough degrees of freedom and the processing capability to generate these kinds of parallel transmissions, which will not interfere with one another. So these are all going on in the same time and frequency. Okay, this can of course also be thought of in the uplink as well. Okay, On the uplink with a slightly different orientation is that the receive beam is what is targeting this particular direction. Remember, these are more logical pictures. Don't take it to heart. Okay, it's more of an analogy. The actual RF situation is a little bit more involved, but we don't want to get into that and confuse. So this is good enough for understanding, just to make sure that there is more to it than just these beams. In FR2, of course, we are not necessarily going to serve multiple users in the same resource block. We don't have the spectral constraints there. The constraint in FR2 is more of the coverage constraint, because when we move from, let's say, a frequency like this to a band like this, we are facing minimum this loss. And remember, there is more. Okay, this is just what we call as the 1 meter loss. There could be other losses as well. So how do we solve that problem, right? So there again, we have a similar idea as what we talked in massive MIMO, but now we are just dividing the space into very narrow directions, so that it's like almost like when you reduce the angular range of a spotlight, that spotlight can carry farther away. Okay, so instead of an example of a 3-sector implementation sometime back, if we did the same thing, that would be our coverage. Now look at our coverage when we have done finer beams. Okay, so these are all easy to draw, visualize, but how do we get this working in practice? That's the question, right? So there are different beamforming approaches, and there is always a lot of confusion. For those of you who are deeply technically inclined, I would strongly suggest please go to this YouTube channel. It's run by very friendly professors who go explain these things in a very, very simple way from a mathematical perspective. So for folks who are very inclined from a, want to get to the heart of these things, ultimately it's all maths. We can only draw these pictures to simplify and explain. So all those beams, how can we generate? So in the very initial days of beamforming, people were using what are called as analog beamforming. So analog beamforming is a very simple idea, very effective, where we do all the interesting stuff in the analog domain, as we call. For those of you inclined, it's post the digital to analog converter in the transmitter side, pre and A to D in the receiver side. Okay, it has its limitations, but as you can see, this was how we started. It still is very useful. Why? Because if we want to go to full digital beamforming, which is very what you call friendly from the ability, see, analog beamforming at one given time can generate only one beam. A pure digital beamformer can generate potentially multiple beams. So if you want to do all those multi-user MIMO, you need digital. But then why are we talking about this when this is there? It's simply because there is a lot of complexity involved where we have to run multiple digital to analog converters, etc. So there is a lot of complexity and cost involved in this. So people sometimes go for this, sometimes go for this, sometimes even go for a combination called as hybrid, where they combine digital and analog. Let me take you through that in a little bit more detail. In analog, remember, the simplicity is that one DAC, one RF chain sufficient for your multiple antennas. But remember, at any given time, you can generate this beam or that beam or some other beam. Okay, these phase shifters is what will help you generate those beams. These are all analog implementation. You can control them digitally. If you do digital beamforming, you need the multiple DACs, multiple ADCs, multiple RF chains. You can generate multiple beams in parallel. Okay, that's the advantage. Complexity of all this, excuse me, is what you have to factor in. Okay, and if you do hybrid, then you can decide, I have so many antennas, but I don't have to digitally beamform on all of them. I might do a subset digitally, and then I might do some in analog. Okay, so many practical systems do try to combine these two. Okay, So that is why you will see some language of hybrid beamforming being used. Now, what we must understand is that whenever we talk about multi-user MIMO kind of systems in this OFTM context, remember that that has to happen what we call pre-FFT. So all multi-user MIMO related processing has to happen pre-FFT. Okay. So this is important for some of you who might have listened to my colleague Devdas on ORAN implementations. You might have seen some splits where they do something in DU, something in RU. You might be wondering, why are they talking about all this complexity and bandwidths and all those stuff? Because there are certain implementation nuances. Okay. And if you don't want to do full-fledged beamforming, simply because, remember, we have drawn very nice pictures saying you can do this and so on. But these do need some channel information so that you can do this for the particular user to whom you're transmitting, right? So instead of getting very deep level information, if we can get slightly coarser information, which will tell you the user saying that, hey, I'm receiving the strongest signal in this beam, that is also sufficient for you to get started. So we call that as beam steering, where we don't have the full-fledged channel information between the antennas here and antennas there, but we create some, you can say suboptimum level of information sharing. So to summarize, how do we use all of this in 5G in NR operations? Is that very first steps, because remember in FR2, right from the first steps, we can use this beam-based operation. So we do beam sweeping, synchronization, random access, etc. Okay. We can then, this is just focusing on the particular user. The base station might be sweeping multiple beams. This user works with the base station on a coarse beam to complete some of the initial steps, and then it can fine tune the beam. You can see progressively how this beam is literally fine tuned. So this is where the new reference signals, all those things come in handy. Okay, remember this whole set of ideas are applicable both to FR1 and FR2. In FR2, this is mandatory almost by default from step 1. FR1, you might not need it in step 1. But in FR1, you might need to fine tune this beam for this user, and you will simultaneously be shooting another beam to another user. That's what we would call as multi-user MIMO. Okay. So that hopefully gives you an idea of the importance of this. There is a lot of, you could say, deeper mathematics behind this. We do try to simplify it by putting these beams, because unless you have access to those mathematics, it might not be wise to talk about things without either getting into the exact ones, or just saying that, okay, we live in an abstract world, and then we'll look at these things sort of in a simplified view. Okay. So that was one of my important targets. So in the last 10 or so minutes that I have, this is of course the first level comparison given by 3GPP between their LTE and NR MIMO. Let me focus on certain important points. Remember that in LTE, spectral efficiency was the only target, but in the case of NR, not only enhanced spectral efficiency, but also FR2 coverage. And that gave rise to all these beam-based processes that we talked about. This is the interesting new stuff, especially for FR2. This becomes critical. Better support for MU MIMO, as you can see here, compared to LTE numbers. And not only, I would say, better support purely in terms of the max layers, even in the reference signals, right from day one, there is a 32 antenna port reference signal defined in NR. This is only a recent development in LTE. So in LTE, you will find it not in the early releases. Okay. So overall, LTE kick-started us on the MIMO path. NR just comes and fine-tunes it for FR1, especially with a strong focus on MU MIMO. And for FR2, it brings all these beam-based businesses so that coverage-related enhancements can take place. So the last part of my discussion is a very nuanced topic, which is called bandwidth parts. Now, what is this business about? And for this, let me kind of just step back and tell you a story on LTE, which is not necessarily that easily sort of digestible. So interestingly, many of you know that in LTE, operators were given deployment flexibility in the sense that the channel bandwidth can range from 1.4 to 20 megahertz in, of course, discrete steps, right? But the mobile had to always support up to 20 megahertz. Now, this is slightly non-intuitive because this one tends to be the more cost constrained, complexity constrained part of the business. Here, you are actually giving that flexibility. Incidentally, that was from the spectrum perspective that this flexibility was given. But from the complexity perspective, there was no flexibility given. So your phone operating on a 5 megahertz network still supports 20 megahertz. Okay. Now, why did it so happen? From the technical parlance, certain channels and certain system information were available over the entire bandwidth. So if this guy was 20 megahertz, if you were 5 megahertz capable, you could not process certain channels which were critical for operation. That's the story, right? Now, we did not run into any problems with this particular aspect because people expected, oh, I want mobile broadband data. This seems to be a reasonable bandwidth to support. Where we ran into trouble is when we thought about IoT, right? And when we thought about IoT, we ran into trouble because there we had no way of selling 20 megahertz IoT RF. The other part where we also got into trouble was when we wanted to increase bandwidths over 20 megahertz. We couldn't enlarge a single carrier's bandwidth over 20 megahertz in LTE. We had to go to carrier aggregation. So it actually hurt the infrastructure because carrier aggregation involves some complex signaling. Though it is implemented today, remember it has a price. So learning from all these lessons, 5G decided we will have to work more flexibly, give some space for these guys to innovate to operate at different bandwidths, allow these bandwidths to be expandable, etc., etc. So that's the motivation for bandwidth parts. So here you can see that the carrier's bandwidth could be much larger than what the mobile is capable of supporting. And you could have different mobiles of different capabilities. And mobile need not keep all this RF front end open. It can go to a low RF footprint, I mean, internally with some power saving when it doesn't have that much data. When you want to isolate services over a large bandwidth, you want to support non-contiguous spectrum. Remember, in the future, we might not get a clean, nice spectrum all the time. We will get some people sitting in between. So we are making a futuristic technology. Okay? We even don't know what is there. This, at least we know something is sitting in a gap. We might be operating. So for all these reasons, bandwidth parts become a very important idea. Okay. Example, the carrier's RF bandwidth could be 100 megahertz, 400 megahertz. Here is some guy sitting on absolute minimum required, say 5 megahertz, suddenly sees a bunch of data coming to it, can switch its front end to process 100 megahertz, finish that, go back to its 5 megahertz or 10 megahertz, whatever the case might be. Okay. So this is the idea from the UE perspective. I already told you from the carrier perspective also, there is a lot of interesting ideas there. Here is again a complete summary here. You start processing your initial signals called as SSP with the initial bandwidth part. You'll be RRC configured to operate on some. You can go to a different bandwidth part when you get, with different numerology potentially, and then you can come back to something. Okay. So you need not operate always in one bandwidth part. You can switch, you can default. All these possibilities are interesting futuristic possibilities. So with that, I come to some of the last things. Though I didn't officially put this in, I think there is also very important enhancements in the hybrid ARQ mechanisms, both on downlink. Here I'm just talking about downlink, but both on downlink and uplink. Most important is it's very flexible HARC. LTE had very rigid time relationships. For those of you who recollect, 4 subframes was a magical number between the data and ACNAC, and then in some cases, even the retransmission, right? All that goes for a toss. 5GNR is very flexible about how to handle the whole HARC business. And that helps for a lot of, you can say, low latency kind of handling. And that comes from this original principles outlined in a very nice Ericsson white paper way back when they're going in the 5G path, saying that we don't want to get stuck in always on transmissions. We want to minimize that, right? We want to make sure a user can decode everything within their bandwidth, which includes their reference signals, control channels, etc., etc. So you could have a 400 megahertz carrier. I'm a 20 meg mobile. I want to operate in this region. I should get everything that I need here, right? And that I could hop back and forth as we saw in the bandwidth part. And the final one I talked about, avoid very strict timing relationship, because that makes it very inflexible when you want to do something outside of that timing. Like when you say, oh, if data comes here, HARC has to come here, that limits your flexibility in doing something on top of that. Okay. So concluding, as I said, it's always nice to look at what LT and NR. We made this slide some time back, so there could be a few typos here, so bear with us, okay? Remember, LT was almost always sub 6 gigahertz. In fact, I was reading through some implementation. It's predominantly sub 3 gigahertz, okay? 5G is embarking on the 3 to 7 gigahertz in FR1. That's the new spectrum range. And then, of course, the more exciting FR2. Large bandwidths, even more to come. Remember, we are not yet done. This is only release 15. Release 16 has also not changed these numbers, but don't expect 17 and 18 to stick to these numbers. Carrier aggregation, almost by necessity, because 20 megahertz. In the case of 5GNR, yes, carrier aggregation is allowed, but I think we will embark less on carrier aggregation compared to 4G. Flexible subcarrier spacing, remember, cornerstone of the most granular element for handling all those services, bands, bandwidth, etc. Very similar waveform, OFDMs with cyclic prefix. For those of you nuance, SCFDMA was a little bit of a drag in LTE. That's also coming back to OFDMA based with an option for the SCFDMA. Okay. Initial days 256 QAM. Of course, LTE latest releases can also do this. This will also catch up on that. Okay, these are just more the FFT sizes that are allowed. Okay. And of course, subframe, etc. we talked about. This was some target latencies in LTE. Of course, this is the magic number here. Remember, slots are very important for 5G because we have those 14 symbol based slots, and sub-slot allocations are also possible. Though I did not go into it, a major change in error control coding, LDPC, supports high data rates with control going polar. Okay, this is a very important change. Even initial access steps, very important for FR2 with beamforming. Okay. And MIMO, of course, 8 stream, 8 or rather 8 layer, that remains the same, but more MU MIMO support. And for those of you who might have not heard it, front-loaded DMRS is much more important for low latency services. And remember, the dynamic or flexible QDD is the new addition, which gives us capability to handle lots of interesting things, especially in small cells. Okay. So just to summarize, new frequency ranges, okay, numerology, large channel bandwidths, especially in FR2, but even in FR1, all those massive MIMO, etc., all those flexibility in the TDD, OFDM symbol, etc. And the whole idea is to prepare the 5G NR lower layers for achieving lots of goals, because we can't go back there and tweak as we embark on this 5G journey. Okay. And that just tells you the summary for those of you who might be interested in certain deployment aspects. There are those things. I'm not interested in covering those things, but just to give you big numbers, that's what I'm interested in. Scalable subcarrier spacing, we talked about it. Subframe slots, and some of these are slightly just leaving you with a nice technical summary, I hope. Okay. So I think now we are ready to address questions. So I hope it was useful for the
Hi,
folks.
Shikant.
Yeah.
Thanks for the wonderful
Sorry.
session. So
Yeah, I
before we
think.
proceed with the questions, so we can stop for a couple of minutes and then just ask people to fill the feedback form. The
Please.
feedback form is being shared by Kuldeep, my colleague. So request you to click on the link and fill the feedback so that we are aware of how you felt about this course. And then what you can do is, because we have around 340 people in the session, so we will not be able to unmute all of them, right? So we can take their question one by one, and we can ask them to raise their hands, and we can unmute them one by one so that we can take up their question. So if you have any questions, please raise your hands and we will unmute you, and then you can ask your question.
So while they are working on their feedback, I am going through the chats and I'll pick up some questions
So
which are relevant.
We'll take 2 minutes. We'll ask.
Yeah, let them go. Let them. I'm just going to choose some questions which are relevant for our topic, because there are some out of syllabus. So I'll skip them, and maybe our people will come back. The right experts will come back on some of those questions. But let me pick up some very NR relevant questions.
You can.
I'll anyway do it after 2 minutes.
Yeah, please just take 2 minutes to fill the feedback form. The link is being shared by my colleague Kuldeep. Click on that link and fill the feedback form. We'll take up the question in 2 minutes. And meanwhile, we also have a paid session coming up in a couple of weeks. You can actually click on the link and also check out more details about it. So my colleague Kuldeep will share the link for the course as well. So you can reserve your seat, and there is a special offer for today, and you can send me an email. I will revert on those details, right? So if you have any question, there were a few questions which are being asked in the chat box. So I will reply for all those questions in the chat, in the email, right? So please feel free to write us an email, and we will actually answer all your queries. And if you felt good about the course or bad about the course, please feel free to give your feedback in the feedback form with a link which is being shared by my colleague Kuldeep. So there is a question about the slides. We will not be sharing the slides, but the session recording will be available on our YouTube channel. You can subscribe to our YouTube channel, and it will notify you when we will upload the recording on the YouTube channel. Yeah.
So can I get started with some questions, Sanjay? Is that okay now?
So let them continue, and you can start with your questions. Yeah.
Okay, so let me slowly do the questions while you fill in the forms for Sanjay to make sure he has all the information. So there's a question about, can we use FR1 for control and FR2 for user plane? Absolutely possible. This is a question from Anupam. Definitely, yes, this is one of the possibilities that you can use something for. When we say control, we should be clear about it. When we say control, I'm assuming at some level where you can keep a link which can, at an application level, be a control, and it can be having the high data throughputs through FR2s. That's possible. Okay, so you can't send PDCCH for FR2 and FR1. If that is what you mean, then that's not there. There's a question from Minu about with FTTH and NR, what are the impacts? So remember that I mentioned that NR also has fixed wireless access implications, especially I think possibly with FR2, but even with FR1 in some countries, because in many places, especially now, I think COVID has accelerated this. Wherever we can't get a physical fiber into people's homes, there is a possibility that this technology can help. For example, if you take India, for example, we are not going to get fiber into billions of houses or hundreds of millions of houses within the next 5 years, right? That's literally going to be a very difficult task. So we need to use a combination of possibly fiber and possibly some of these technologies, okay? There was a question about spectral efficiency differences between LTE and 5G-NR. I thought that was interesting. It's a slightly more nuanced question because if you look at it, and in fact, there are results presented by 3GPP in their evaluation. See, one of the main tenets of 5G is that we are allowed to do large bandwidth channels. Even if you take FR1, which is the fair region to compare with LTE, LTE by design is limited to 20 megahertz. Whereas in our case, we can go 100 megahertz, and that way we are able to utilize, if you want to do the equivalent spectrum in LTE, you are looking at 5-component carrier aggregation, which has a lot of difficulty. So there are nuanced, you can say, spectral efficiency enhancements, but the more gross spectral efficiency enhancements could come from massive MIMO based MU MIMO. Okay, that's where the real step forward for 5G is there. Okay, remember that LTE advanced releases are also incorporating some of this, but they can't cater to all the LTE mobiles out on the field. Whereas 5G from day one is going ahead and supporting this. Okay. Let me see. Is there anything else which I would like to comment on? Sudhir has a question of how many TX and RX antennas at the base stations and on mobile. Macro cell antennas, people have at least claimed 64, 128 massive MIMO is a claim. On the mobile, it's a little bit more smaller. 2 and 4 antenna kind of mobiles are probably the limit. Okay. Where else? I don't know if I've missed anything here. I'm only taking some very NR specific. So Nitin's question is related to core set. Core set is the control region set. Basically, this is an enhancement to the PDCCH concept in LTE. Slightly more deeper topic. So maybe because it would need also time. So core sets basically allow us to define regions in time and frequency where your PDCCH is going to be present. So it's like, you can almost say it's like using the bandwidth parts idea very specifically for the PDCCH business. So you don't have to go searching everywhere. Okay. So user is usually configured with some core sets and they only go and search or watch out for those. Kishore, will dynamic TDD get impacted with ducting interference? It's possible. In fact, a release 15 enhancement was primarily designed to address that. Again, since it's an involved question, you're welcome to write to us on whatever links Kuldeep and Sanjay have supplied. I'm happy to see whether I can send you some detailed information on that. Is there anything specific? I think I'm done.
There are a few questions at the end, Shrikant, if you would like to have a look at that.
Yeah, so I'm avoiding anything from the NSA, SA, etc. I'm only answering the 5G NR specific.
So I think we can take a couple of questions if somebody would like to ask those questions. So he can raise their hand and then we can take up those questions. Anybody would like to ask any questions? Raise your hand. I'll unmute you and then you can ask your questions. So there is a question from Amar Agami. Amar, please unmute yourself and ask your question.
Yes, I would like to ask for the distance that can covered by FR1 and the FR2, and how can we can imagine if the millimeter waves with high frequencies can cover. So we need to implement more sites in RAN domain for that.
That's correct, Amar, because typically FR2 coverage, again, remember that more than distance, we usually will talk path loss, etc. It does vary a lot in on an environment basis. So typically people are using these FR2 at least in the more, you can say, traditional deployment, they are using it primarily for hotspot kind of areas, which will serve, these days about several 100 meters of cell radius. Okay. Whereas your typical FR1 deployment can cater to several kilometers in a classical deployment. However, remember FR2 with special antennas on both ends are being
Okay.
targeted for fixed wireless access. So it would depend on how the operator is using FR1 and FR2. Again, we do, luckily, I mean, when I say we, there is public domain data which is available from some deployments. Again, if you maybe write to us, I can share some of that, which does show some interesting aspects of how people are using FR1 and FR2 in the real world.
Yeah, Mayank, please unmute yourself and ask your question. Mayank, you can unmute yourself and ask your question if you have any questions. Manish, you can unmute yourself and ask your question if you wish to.
While we wait, I can also answer a couple of them. How does DMRS impact throughput?
Hello.
Yeah, go ahead, Manish.
Hello.
Yeah, go ahead, Manish. I can hear you.
Yeah, I'm audible to this is Manish.
Go ahead, Manish.
Hello. Okay.
Manish,
So
we
my
can hear
question
you.
is that I have seen in vendor that they are using like sieve for sieve, and they are using digital beamforming, and for FR2 they are using hybrid beamforming. So any logic behind that?
There is a logic behind that, simply because in the high frequency, see, the targets are also slightly different. As you remember, I said in FR1 we do more multi-user MIMO, and remember I explained that's why I specifically considered when you want to get MU MIMO advantage, you need digital beamforming. Okay, digital beamforming is the key. Whereas in FR2, remember that the focus is more on coverage. And for coverage, it's not that important to only do digital beamforming. You can have a bunch of analog beamformed patterns kept ready, which you can choose according to that particular user. So what they do typically in FR2 is to achieve a fine beam, they can do a combination of digital and analog because of the costs and complexity involved. If you recollect, when you hopefully can recollect some of the material, you remember the multiple RF chains, etc., that are needed. That becomes costly in FR2. If you go higher in frequency, the RF becomes much more complex, costlier, power hungry, etc. So you don't want to do as much. And so that's why they limit the digital beamforming there.
Yeah. Brajesh, you can unmute yourself and ask your question.
So my first question is how we decide the number of FFT in during frame structure, and other is the can you explain the DFT as OFDM?
Okay, so let me try and give an answer given our it's an overview session. Just try and address your point. So user doesn't choose FFT, etc. The implementation chooses the subcarrier spacing. Okay, so the subcarrier spacing choice, we gave a few examples, right? Typically, for example, there are constraints of macro cell, small cell, high bandwidth, low bandwidth. These are the constraints that typically dictate what subcarrier spacings that you use. And people have not found, I would say, great reasons amongst those choices in FR1 and FR2. I think we're still waiting for those optimizations to come. There are obvious, you can say some instances, some reduction in time can occur, but then there are other complexities which can happen. So it's not straightforward between the choices in FR1 and FR2, how best to choose something. Okay, that is the first part of your
sir,
question.
I'm asking about FFT.
That's correct. So, sorry, your name, Brijesh, FFT is an implementation. So FFT size for a given bandwidth comes from the subcarrier spacing. Okay.
Yes.
So if you choose, for example, 100 megahertz, and you
Yes.
choose actually 100 megahertz and 15 kilohertz don't go well. So you choose 50 megahertz and 15 kilohertz, then you have a certain FFT size. Whereas if
Okay.
you have 50 megahertz and 30 kilohertz, you have a different FFT size. So indirectly, your question maps to the subcarrier spacing.
Okay. Thank you.
Okay.
And
The second part of your question was just trying to recollect. Brijesh, could you help me recollect that?
sir, I'm asking that can you explain about the DFTS OFDM?
Okay. So the DFT spread OFDMA is nothing but what we do is that it's basically take the data that you want to send. And for those of you who might not be inclined on the signal processing side, you can just ignore. What we do is we do a transform of the data before we actually put it on the subcarriers. And why do we do this is because we decorrelate any data, and that will have good what we call peak to average ratio. Okay. So you
Okay.
can basically, if you don't want to understand the details, think of it as a way by which you can reduce certain peak to average in your data pattern. That is what the DFT spread OFDMA does. Okay. It
Okay.
helps because of the power efficiency challenges on the mobile side.
But in LTE, SCOFDMA perform the same thing. What you are saying that
Exactly.
DFT.
It's the same thing. Yes. In LTE, they called single carrier. Now they have reworded it to DFT spread, giving the exact implementation. That's all.
Okay. Okay.
Yeah.
Thank you.
So Shrikant, we can take one last question and then we can wrap up the session.
Sure. Sure.
Yeah. Shwambu, can you just unmute yourself and ask your question? Shwambu, can you hear me? Okay, no problem. So there is a question from Sandeep in the chat box, which is about AI ML implementation for 5G radio.
Correct.
Yeah.
Yeah, so this is important because what we are seeing with the Open RAN trend is that there is a radio intelligent controller with some real time, non-real time. So the question that we just addressed with respect to what Brijesh was asking, how to choose between the 15 kilohertz, 30 kilohertz. I don't think it's going to be that straightforward going ahead in the future to decide on all these things manually. So people are going to employ these algorithms and decide on some of these things based on previous performance record. Let's say, for example, I had this traffic pattern and this were some of the things which were tried in the training sessions and we got some results. So from those learning, we are going to tune a lot of those things. Okay. So whether it's going to be the TDD splits of downlink, uplink, whether it is 15 kilohertz, 30 kilohertz or 60 kilohertz in FR1, or maybe other parameters. So all these things to a certain extent are going to be driven a lot by algorithms. Okay. So I do not know whether Sandeep had that in mind. So we do expect to see even in the radio domain, a lot of intelligent algorithms, at least helping the operator, maybe not immediately on the real time, but possibly maybe in some non-real time or a slightly longer time cycles fashion. Okay.
Yeah, thanks, Shrikant. So that's all what we had for today. For our past session on Open RAN, there were some questions related to 5G core network, Open RAN, etc. Right. So